Thank you so much. And I guess one of the questions that I would like you to answer at the end is how many puns I have on this title. So on the road to collective intelligence is a Green Light Sonata. Green Light Sonata, you will see. There is a pun in there. So I'm going to talk first about the multi-agent system in transportation. That's where I'm going to start. I'll give you a background about traffic control, operation, and what we do in traffic, because that is going to be very important when we talk about the musical inspiration. There was an aha moment, and I took it from there, and I think it worked at the end, but you'll be the judge on that. And then the methodology and experiments, I'll give you the analysis and results, and finally, my 2 cents at the end of the talk. So in a multi-agent system, and again, this, for me, I was always inspired by the Matrix movie. And when I teach my classes, I tell my students, the first homework is that you have to go and watch the Matrix. And then I get some references from there. But in the transportation system, the way I look at it in general is that I have 3 levels. And the very bottom is the agents, and that's where you can have people, you have cars, you have municipalities, decision makers, and so on. And you have traffic controller, which we're going to talk a little bit more about today. And then you have the system level in the middle, and that's where the interaction happens between all those different agents. And one of the important things we do is try to encapsulate the behavior that matters at each agent level. So the agent, of course, could be anything, could be an individual unit, or could be a homogeneous set of entities that act together. And then on the top, and this is where I'm going to change at the end of the presentation. So I'm starting here, I'm going to end here with a slight tweak. I'm just giving you a warning. This is where the architect, if you have seen the movie The Matrix, and that's where we try to control everything that is happening in the system. And basically, when we're dealing with agent in transportation, it's either that we're doing some optimization to guide some objective function toward the goal that we want, or we are dealing with people which are very hard to control, and therefore we incentivize them, try to nudge them to take some decisions in the direction that we want. So before I get into the depths of the presentation, I want to have everyone on the same page, even though you are all drivers, I'm assuming, and which might not be a very pleasant experience here in LA. But you have been at an intersection at some point in time. And the way that intersections work is that we have 8 different protective movements. You see, 8 different protective movements at the intersection. There is a traffic controller. The traffic controller has 2 rings. This is the first ring on top, the second ring on the bottom, and there are numbers. And as time goes by, if that decision is at 1 and 5, you will see the 1 and 5 being green, and then the controller moves on to 2 and 6, 3 and 7, and 4 and 8. So this is very important for what we're going to talk about. And there are some manipulation of that. So sometimes you can have, the through movement going with the left, or, you can manipulate things and so on. But there are these barriers that we can never cross unless the 2 rings cross them together. So you cannot have 2 and 7, for example, or 3 and 6, because that's going to be a crash. So that's part of the background that we have. And then when we deal with any system like that in transportation, we do some simulation. And one of the packages that we have used, and this is where I started thinking about this, you have the traffic here, as it is going to be, let's see if this is going to make it move or not. Yeah, so as the traffic is moving, and you are controlling that traffic, hopefully in an optimal way, what you will see on the top is the different phases. And as time passes by, it's which phase that is going to be green at that moment in time, and that's how things get simulated. And then we get some objective function. Could be delay, could be throughput, could be anything that we are interested in. Now, I'd like you to pay attention to this and look at it in the next slide, something that looks similar. Now, can anyone guess what this is? That's a score, but like which piece is that important? Like if I... Green light. So it's coming. Green light sonata is coming. It is. Wow. Yeah. So there is some, of course I pre-engineered it, in that way, but the idea is any system that we simulate in traffic, we could have some sonification of it that might mean something or might not mean something, depends on what you're doing. And then, so there was, okay, so something looks similar here. I don't know why it's not working now. I'll do it from here. So that was one point. The second point of inspiration was what musicians do when they are improvising. This is a video of some performance we have done. So I'm the person sitting here, and I'm going to be playing some instrument. And this is Annalise Thomas, which was also a participant in the experiment that we have done. And she's playing a qanun. So I'm going to play this like 2 minutes. You'll hear me improvising. You will hear her going on the background as well. So she's playing. So what's important about this and why that was inspiring to me is the idea that while improvising, a musician, another musician improvise, they haven't scripted anything. And yet there is some sort of a harmony or some sort of a knowing what to do next that is coming from the human ability. I can't explain it myself, and that's a part that I wanted to explore more. And therefore comes the Green Light Sonata. So if you know, I'm sure you know the Moonlight Sonata, right? So now there are some plays with words here. The green light as in green graphic light. And the sonata is also, coming in here as an inspiration from between the AI and the human in this. So sonata is signal operation with Neuro-fuzzy Acoustic Tuning Application. That's where the sonata came from. that word. So the idea here is, if I have traffic, if I can sonify that traffic, and I have the musician improvise in that sense, like what we have seen, and turn that improvisation into the signal control. So depending on what the musician plays, the signal that gets green is what has been played. So there has to be an assignment between what is played and what is actually exists at the intersection. And if we get all that data, then the rest is going to be history, because we'll just take those decisions and encapsulate them with an AI, with the optimal policy learning. So there is a Markov state estimation in the process, and then we can use any of the reinforcement learning, as I will show today, and what results that we got from that. So we start with assigning a musical note to each one of those 8 phases that I've described earlier, and also assigning listening basically to what the musician is playing and determining the green light corresponding to it. And the original work of just building the system and collecting the data is published at the ITSC, the transaction for the conference in 2020. And we integrate basically the simulation software that you have seen earlier with a musical software that transcribes back and forth. So it looks like this. So you have the simulation over here, and we have the detector that are measuring the traffic on each one of the 8 phases. And then depending on how long the queue is, we make that sound in particular higher or louder. And then that gets sonified. We are playing, and what we play, we have the system that is listening to us and converting that back into which phase gets the green. Now the idea is, when you turn the phase green and the traffic starts moving, the queue dissipates, so that sound becomes quieter. And vice versa, whenever you turn a signal red, the queue is gonna build, so it gets louder. So you start hearing that conversation. I have a small video clip that I'll play for you. But you start hearing the conversation between the traffic, like a church music in a sense, because all 8 phases are coming at you, but with different intensity. And what the controller, in this case, the musician, is doing, I was accused at some point that I want to capture all musicians and put them in traffic cabinets so they can operate light, but I said, no, I'm just capturing their behavior. And it looks like this. So let me play this one. Oops. So now you'll hear that's traffic. So that's a correspondence between the two. And basically, we ran the experiment by listening. Every one of us is listening to the simulation that is running in front of us, and also looking, obviously. So you don't know if it's the auditory or the visual signal that we're using at that point. And we have a reference of Webster equation. That's one equation that's supposed to optimize traffic performance. And what you see on the blue here, the visual and audio cues for 3 musicians. I'm not saying which is which. But you see that, like, okay, we're approaching the performance of the benchmark, especially 2 of us here. Yes?
So this is really cool. I never thought I would like to get stuck in traffic. But I was wondering, did you try a situation where you guys are sitting in different rooms and can't hear each other, and you're all following the same synchronized visual cue?
We haven't. And this is a great point, because actually at the end I say that because we are listening to each other, there is a collective intelligence that is being embedded here. But when we started this, we were just exploring, like, is this even gonna work at all? And the part was, after we did the visual, with including visual cues, I was just, on a whim, I said, like, are you up to a challenge? And they were really happy and said, yes. Said, turn the laptops around. We're not allowed to see. And then what happened is that we got even better with the red lines. So there is something in there, and that's what was inspiring, because then we can explore a lot of things based on this. But now come to encapsulating the behavior rather than capturing the musicians and putting them in the cabinet. So the first thing that came to mind is, we can use a state machine. And basically you have the states and the Markov process that takes you from one state to another. And of course, depending on the policy that you're taking that maps the state to an action, that is going to change the probabilities that are happening here. So basically, let's put it in terms of traffic. If this is basically the green of phase 2, and this is the green of phase 4, but your policy is, if you are at state 2, never change, because we have very long queue, or we are blocking the road on the side and we just want that traffic to go, then that's affecting, obviously, there is no transition between state 2 to state 4. But if you are doing it 50-50, then depending on the time you have already spent on state 1, you're going to shift here, or vice versa, or you stay, and so on. So the idea is, if you know the Markov probabilities, you can come up with the optimal policy. If you have a policy, it's going to change the Markov probability, and therefore you need the value iteration to do the optimization of the system. But in this case, the policy here is not the optimal policy that is going to result in minimum traffic, for example, delay, but it is rather an imitated learning. I want to capture what Monty with Zaud is doing, or Annalise or Charles are doing. Right or wrong, that's what I want to get out of it. So basically what we're doing is solving the Bellman equation with reinforcement learning, and we're doing it in a value iteration. And the general idea is, if you get stuck in a certain value of a state, so if you get stuck in a state, the state has a value moving forward from it, depending on the policy that you're following. And also, if you know the value of the states, then you can determine the best action you can take from that point moving forward. Similar to a simplified version would be in a queue learning, where you have a discrete system. And basically, this is the very traditional reinforcement learning, where you have an agent dealing with the environment. When an agent takes an action, the environment responds with a reward and the probability of the next state. And then you are using that to maximize the benefit or the reward over the long term. So you have the discount. You're taking the discount factor into account, and you're taking the estimate of the optimal future values in the learning. Now, the challenge would be with the dimensionality, with the high state dimensionality, but also bringing it back to the situation that we're dealing with. So the training input for my agent in this case was the different musical notes that the musician is hearing at a certain time. So these are 8 different intensities or loudness of the notes. And the ring phases. That's why I talked about the rings first, ring 1 and ring 2. So ring 1 has phase 1, 2, 3, 4. Ring 2 has 5, 6, 7, 8. So depending on those state input, the output is the called phases, like which phases the musician is calling based on what they are hearing. So that's the action. We discretize all the input variables using fuzzy sets, because otherwise you have to visit all the states, and if you are dealing with every state individually without converting it into a fuzzy set, then you might not meet certain states ever. But this way, there is a relationship between whatever that the musician have used at any given time with what is being listened to at another given time. And then the continuous actions, basically I have 2 actions coming out of this. What phase runs in ring 1 and what phase runs in ring 2. These are what I want to get the agent to produce. And this is the Bellman equation, basically, for a stochastic system here. And this is the Neuro-fuzzy actor-critic reinforcement learning framework that we're using. So all the inputs are being, every input variable. So this is note 1 through note 8, and then ring 1, ring 2. And each one of them has the minimum and maximum that was ever met in the training. And then you have all the different rules. Every rule is a different combination between every one of those notes. So rule one is basically the maximum for note one, and or the minimum note one, minimum note two, minimum note three, and so on. But ring two is changing; it's different combinations basically. So I have 10 different state variables. So what I have here is 2 to the power 10 different rules. And then basically I have the actor that is producing the value of the action that is being taken by the agent, and the critic that is calculating the value of the state that the agent is currently at, given the action that I play. So if I play note 4 and I bring phase 4, that's going to be what is coming next. So it want to know, the agent would want to know, in this case, what is the value of phase 4 over the long horizon of training. And so an ideal case here, what does it, an ideal case means? I looked at the data and I said, like, what if I have an agent that actually just want to replicate whatever ring phase has right now. So if it's in phase 2, remain in phase 2. 2 and 6, remain in phase 2 and 6. So if the prediction is very well anticipated, so this was just for me to make sure that my code works, basically, if you will, or the concept work. Can the actor critic produce that? And sure enough, you have like 0.99 R square for ring 1 and for ring 2. And the reason that you have some noise here is that in my training, I said I will accept up to 20% error, because the controller can always just calculate the integer of that. And basically, you will see the agent going up and down, matching the points where the data was saying. So that if the data said that ring 1 should be at phase 1, ring 2 should be at phase 5, the agent is capturing that before it goes on to the next step. So making sure that works, now I wanted to look at the real data of what the 3 musicians played. And if you are ever curious about what those instruments were, so the oud is here. I have one, by the way, I'll bring during this workshop. Feel free to party with me before we leave. And there is a violin. Everyone knows what the violin is. And the qanun is this instrument here, like 76, I think, strings. Very hard to tune before you start playing. But once you do, it's really beautiful to listen to. And this is the agent performance being trained to the musician actions, in this case, the real actions that were taken. And you see that it converges very quickly, actually. And the 2 lines are for ring 1 and ring 2. So it is doing well for both rings. There is a little deviation here in this one, but actually ultimately reduces and get really good values. And this is the action of the oud. I picked up on the oud player for some reason. But this is zooming in, and this is for one of the rings. So you'll see that the blue dots are the actual data, and the lines are what the action being trained is trying to estimate what those data should be. So it's actually doing pretty well. And the R square. Yes.
So I'm trying to kind of orient myself over here in your talk, right? So clearly what you're doing is fascinating and very creative.
Thank you.
But are you thinking about it as kind of like a traffic flow problem, or are you thinking about it as how are humans harmonizing problem? It's that aspect is not quite clear to me, right? You're showing that musicians are training themselves to this particular form of cue data. So maybe it's a universality of music that you can kind of explore. So which aspect are you more in harmony with?
I'm interested in both. And that's where the augmentative intelligence and the collective intelligence comes in. In this case, I want to capture what the musicians are doing in response to traffic so that I can solve the traffic problem, because all 3 of us were actually doing better than what we currently do. So there is obviously something there that I want to capture. It's not ending yet, of course, we can always do better, but in the process, and of course, there is also the fascination of what the musicians are doing and what they are, especially that, I play, but I don't know what I'm doing when I'm playing. So I'm interested in knowing that, yes. And then here, look at the full data. So with the oud, how it is, again, this is time, and this is a different phase in ring 1, and this is the different phases in ring 2. and you'll see how the trained agent is capturing the data very well. It's going up and down and so on. Same with the violin and same with the qanun. So now we have checked that claim. Like if we have the data, can we train the agent that is capturing that, encapsulating that behavior? And then you can actually use that software now and put it in a traffic controller and let the musician live free. We're not capturing them. This is another thing that I just wanted to mention, because the idea of, why are we interested in the actor-critic reinforcement learning to start with? And can't we just do some statistical modeling, for example? And there was one other project that I did where I was trying to capture the behavior of drivers when they get in a strenuous situation. They are trying to avoid an accident. And this driver in particular is going down and then coming back and continuing. And I'm getting this data, and again, the agent is being trained and capturing that very well. This paper came at the end of the project when I thought, like, I'm trying to strike my ego and thinking that, hey, we developed something really cool. Let me run it with just the statistical analysis, the boring stuff, to find that I can't do the statistical analysis very high R square as I did with the agent. That's what I thought. And then I ran the statistical analysis and I came up with a higher R square than the agent. So I was depressed for like half an hour maybe. It's like, all this work that I've done, and I could have just done it with statistical analysis. But then I looked at what the statistical model is telling me, and it was saying that with that very high R square, the acceleration is equal to 0.9935 of the previous acceleration value. So what the model was telling me is that once this driver is decelerating, they are going to continue to decelerate until they stop. But the data is obviously saying otherwise. So the idea is that inflection point, if you are using a statistical analysis, is just 1 point. If it doesn't capture, the statistical model doesn't capture, it's okay. It's just 1 point. It's still going to give you a very high R square. But when you're doing it with a state machine and you're solving the Bellman equation, then you know the value of the state. And you know that this state, if you ever get stuck in it, you're not going to, you can take the wrong action. So you avoid, you account for it in the building of the model, basically. And now, how does that work here? In this, well, I don't know what the statistical model is going to tell me, but what I know is that I trust this more than I trust the statistical model, as long as I capture all these behaviors. And this paper was published like 10 years ago. You can have a look at it to see. So where are we going from here? And basically is incorporating the human factor into this whole process, because in terms of transportation system, humans are part of the demand side, because you can see that whatever that human behavior that needs to be encapsulated, and if it is not encapsulated correctly, then you end up with all of these different crashes and safety problems. So obviously we need to capture that in the agent, so getting the behavior. So it's not always about minimizing a certain function or maximizing a certain objective. It's about the imitated learning and capturing the actual behavior. And then the same thing, so here is what I'm hoping you have seen this video already, but basically turning what we do at the supply side in traffic controllers by incorporating the human aspect, and then looking at the technology and the things that are coming next with the human to everything else, the Internet of Things, or in this case, traffic controllers and other vehicles, connected vehicles, automated vehicles, and so on, that could eventually, in the future, basically remove the traffic controller or have a new version of traffic controllers. I think it's playing, but it's taking a while to show here. But basically, if we are now changing the traffic controller, we cannot change it in isolation of what is actually happening on the road and the new technology that is going to be implemented there. So again, another case for collective intelligence in a sense. And the real good question that came earlier in here about, or from Ida, right? How the musicians are listening to each other or not. So I'm saying here, now this is, we are listening, but we are doing it together. There is something cool about the Qanun every time I see it. Everyone is having their own objective function, but everyone is listening to what others are doing. And with music, there is this dissonance, right? Like if you, looking here, before we look at what does that mean for the system, oftentimes when you have musicians playing together, and if there is a singer or the orchestra leader, if somebody does something wrong, they can look at them and immediately, right, there is something wrong coming from this side over there. So can we have that harmony instead of that architect sitting on top just with an objective function that looks at everything collectively in a collective intelligent way? And so as a conclusion, basically, let's not forget the human intelligence, because when we think about collective intelligence or think about different agents, the humans have a lot more wisdom that we can incorporate here. And as far as transportation is concerned, I'm thinking that there's going to be a paradigm shift, because we usually used to talk about intelligent transportation systems. Basically, the use of technology in doing everything that is related to transportation. But I think it should be changed to smart transportation in collectively intelligent systems and taking everything together. That is, if we do that paradigm shift, is going to lead to the doing different things now at the agent level linked to new design, objectives, and performance measures and metrics and so on. So I started by saying that I like the Matrix movie, and if you haven't seen the Matrix, you have to see the Matrix. And I end with a quote from the Matrix that I don't know the future. I didn't come here to tell you how this is going to end. I came here to tell you how it is going to begin. Thank you very much.
We have plenty of